Hello and welcome to this session going over correlation and regression for week 4. I know I met with many of you earlier in the week to go over the exam, but I just wanted to have this session so that you have an overview of correlation and regression. So just starting out, obviously in this class we're dealing with quantitative research, and at this point in the course we're looking at inferential statistics. One of the quantitative methods that you can do is to look at relationships between variables. So for example, with a correlation, we do look at relationships between or among two or more variables. So when we have a correlation, we often use terms like relate, relationship, association, or trend. And we look at whether those are related and to what extent. For example, is there an association between age and job satisfaction among registered nurses? Are parental education levels related to academic achievement levels of high school students? So in these examples, our sample is also mentioned in the research question, but we are looking at the relationship between two variables and looking at the strength and the direction of those relationships. One thing I do want to point out is that if you go into SPSS, there is a statistics coach, and that will allow you to play around a little bit with correlations. So for example, there is a statistics coach that looks at correlation, that is identifying the significant relationship between variables, and you would then choose scale numeric data, because with these correlations we are looking at continuous variables. That's always preferred. So when you're designing your study, if you can have a question like age, you would always be better off just asking what is your age and having people write in their age in years, rather than having a categorical variable, because you have so many more options in terms of analysis. But of course we can do correlations with some different types of variables as well, but the kind of the classic basic correlation design is looking at two scale or numeric variables. So again, we're going to select that we have two, at least we typically have two variables that we're correlating, and we want to display that by tables and numbers. And then this will walk you through the steps of what you need to do. So I just wanted to point that out because it's just kind of a helpful tool, and some students like that because it can give them some additional practice. It also shows you what kind of charts you would use. With a correlation, we do a scatter plot. I know a lot of you have been doing box plots and histograms, but with correlation and regression, you always should have a scatter plot. So this tool will help you figure out how to do a scatter plot. And there is also a video that I put in the classroom that shows you how to do that in the helpful resources folder. So what is a correlation? We already talked about this a little bit last week. Correlation is looking at the strength and the direction of a relationship between two variables. There are instances where it can be more than two variables, but again, our kind of basic correlation looks at two variables. It doesn't distinguish between explanatory and response variables, so it's not like there's an independent variable and a dependent variable. It's just looking at the relationship, like what's the relationship between aggressive behavior and watching violent TV shows. It could be that watching violent TV shows leads to more aggression, or it could be that more aggressive kids watch more violent TV shows. correlation doesn't distinguish between those two, it just looks at the relationship between them. And it'll give you a value ranging from -1 to +1, where a 0 means there's no relationship, and a 1 indicates that it's a perfect relationship, either positive or I'll talk about that in a minute. The scatter plots show us if there's a linear relationship and whether there's some inferential points or outliers. It can be rather sensitive to outliers, so that is something you would typically want to look at before you do your correlation analysis. And then we're also going to talk a little bit about regression because correlation is part of regression, and regression is our other topic for this week. But in terms of correlation, just sticking on that for now, the correlation coefficient is a measure of the direction and strength of a linear relationship, and it's calculated using the mean and standard deviation of both the x and y variables. The correlation ranges from -1 to +1, and as I mentioned before, we can look at the strength and direction. So the stronger relationships, it's going to be a very straight line, right? At least not much correlation is going to be dots just all over the place. Like here we can't really see a straight line. You can see as your correlation gets bigger, here's a correlation of 0 to -0.3 to 0.5 to 0.7. We can start to see the stronger the correlation gets, the closer the dots are, or the scatter points are to the line. So again, correlation looks at linear relationships, so we want to see if it follows this diagonal line. The strength is how close the points are to the dotted line, and again, you could see here like a correlation of -0.3. The points are really not that close to the line. But the closer we get to 1, this is essentially a perfect correlation. The scatter points are all hovered around the line. The direction, so that deals with, the strength is the closer it is to 1 and the closer it is to a straight line. It doesn't matter if it's a +1 or a -1. The strength is how close it is to 1 or -1. The stronger it is, the closer it is to 1. The direction is positive when individuals with higher values on one variable also have higher values on the other variables. So more time watching violent TV, more aggressive behaviors. Those two, as one increases, the other increases as well. The relationship is negative if as one variable increases, the other variable decreases. So, the more time spent studying, the less errors on an exam. So as one variable increases, the other decreases. So that's how you determine whether it's, negative or positive. So correlation deals with the strength and direction, but again, it doesn't have predictability. You can't predict one from the other. It's just looking at the relationship between two variables. On the other hand, with regression, we can look at some additional information. So correlation is part of regression, but regression is a little bit more sophisticated in that we have more information. So regression allows the assessment of the relationship between a dependent variable and multiple independent variables. So we can have more than one independent variable. And we can look at what the relationship is of several independent variables to the dependent variable. And we can even determine whether, if we add another variable, if that adds to our ability to predict the outcome. So that's kind of cool because we haven't seen that before. So for example, if I wanted to look at whether depression and stress relate to obesity, I could get information about how well those variables predict obesity. But then I may realize through reading the literature and through other things that actually the extent to which people emotionally eat predicts obesity. So I could say, well, if I add that variable, if I add emotional eating, does that also predict obesity when I have stress and depression in the equation? And does it help me predict it better, or does it not add much? So there are different statistics that we'll be able to use to answer that question. So regression is usually used to predict, whereas correlation just looks at the relationship between the variables. And ultimately, with regression, the goal is to find out how much each independent variable contributes to the prediction and come up with the best equation that predicts the dependent variable. So again, in that example I just gave, I could say, which is the best predictor of obesity? Is it emotional eating? Is it depression? Is it stress? Of course, it could be some other factors too. There could be other health or genetic factors, but let's just say of those three variables that we've measured, which one is the best predictor? Is it depression? Is it stress? Is it emotional eating? Which of these predict the dependent variable and which one is the best predictor? So one thing to consider with regression is, of course, we could have any number of independent variables theoretically, but we have to limit it because the more independent variables you add, the more participants you need to have. So the number of cases or participants you have to the number of independent variables you have must be large, or at least to have sufficient power. So the more independent variables you have, the more people you should have. In terms of the dependent variable, the greater the skewness of the dependent variable, also the more cases you need. So as we've talked about before, your dependent variable with ANOVA and t-test and regression should be approximately normally distributed. But if you have a very skewed dependent variable, then you also need more participants because, regression can handle a certain amount of that, but if it's more skewed, then you need more participants to make sure that you're getting accurate information. But of course, the flip side of that is too many participants can also be a problem because it can lead to significant results. In terms of outliers, those can have a strong impact on regression, so it is something we need to look at. Again, our options when we have outliers are to delete, rescore, or transform the variable. I'm going to go through an example with this. And in terms of finding outliers, we look for frequencies and box plots, skewness, kurtosis, z-scores, and for a bivariate regression, we use Malinova's distance, but that's not something that's required in this class. So our first step is to find outliers, whether we're looking at correlation or regression. We're going to want to look at our data descriptively. We've talked about this before, that we always start out with getting a descriptive look at the data. And one of the things that we do when we're looking at our data descriptively is to see if we have any outliers. SPSS will almost always flag potential outliers, but it doesn't mean that it's significant or anything that you need to do anything about. So if you do determine that you have legitimate outliers that may be impacting your data, your correlation or regression, you have to decide what to do with it. For the example that I'm going to talk about today, the potential outliers were not deleted, but that is an option. Again, with your assignment, I don't want you to do any of these things. I want you to just tell me what you would do with outliers, but not to actually do these things, because I don't want that to be confusing. And then next we're going to look at an example of a correlation, and then an example of a regression. So here's an example of outliers, potential outliers. So we have a scatter plot here looking at number of admissions to the Children's Museum. And this scatter plot represents the number of children against the number of admissions to the Children's Museum. So does having more kids predict how often one goes to the Children's Museum? So for the next few slides, we're going to focus on three tables, the case processing summary and the descriptives. As you can see here, there's also a test of normality. We also get, when we do box plots, we get the skewness and kurtosis. So we get a number of different things. So the first table I'm going to talk about here is the case processing summary. And from this table, we know a few things. We know that we had 465 participants. We know that we don't have any missing data. And we can tell that because of looking at the valid and the missing data. In terms of the descriptive statistics, we can see that the skewness, both of these variables, the number of admissions to the Children's Museum and the number of children, they're both positively skewed, but not necessarily problematic. However, you can see, of course, you could see here that our data is very skewed, right? It's not normally distributed. We could see we have a high, positive skew. But we can also see that we have a potential outlier here. So for this variable, how often, number of admissions to the Children's Museum, you can see that there's a case or cases that are around 80. So we can see that that looks like a possible outlier. Whereas here, for number of children, even though it's skewed, it looks fine. And obviously, it's legitimate to have 12 or 14 kids. Doesn't happen that often, but I know people who are from big families with 10, 12, 13 kids. So it happens. It's out there. Obviously, most people are more here in the 0, 1, 2, 3, or even 4 kids. But these are legitimate cases, so there's not outliers for the number of children, but this number of admissions to the Children's Museum is definitely something we would want to check out. In terms of outliers, again, SPSS does provide a table with what they call extreme values. And so in this box, you can see that there's the two variables, number of admissions to the Children's Museum and number of children, and they highlight for you what possible outliers are. But again, these are not necessarily outliers. These are just possible or potential outliers, okay? So the nice thing is that it provides these numbers so that it's easier to find. But as we just talked about, like with number of children, there's a lot of people who have one kid. That's fine, that's legit. I think this was a study where everybody had kids, so, or wait, actually they say they don't necessarily include the zeros here, but these are legit. These are potential outliers, but obviously there's going to be a lot of people who have one kid, or there's going to be some people who have a big family. And then in terms of number of admissions to the Children's Museum, of course, unless it's a requirement to have gone to the Children's Museum, there's going to be people who haven't gone to the Children's Museum. So that's why it shows the 5 highest values and the 5 lowest values. But let's check out this, which was on the graph, that there are 2 very high numbers. Well, 81 visits to the Children's Museum is quite high, right? That means going more than once a week. But some people, might live next door to the Children's Museum. Maybe they use it as like a playground or a place to go when they don't have anything to do or when it's a rainy day. So it's possible. It's not so far from 75 or 60, some of the other high numbers, but it is very high, and in that previous graph, it did look like a possible outlier. So one thing we want to do is look at the normal distribution, and we already know, we don't even need to do this test, but it's statistics, so we will do the test. Whether it's not normal, we know it's not normal just from looking at that graph. And since the p-value is less than 0.001, we know that it wasn't a normally distributed variable. Either of these. This table shows both the admissions to Children's Museum and the number of kids. But I just want to go back and say one other thing about the outliers, because the kurtosis for this Children's Museum one was quite high, 13.101. If you recall, we said to look around 3 or 3.3, depending on the sample size, and we can see that there's, at least a value, possibly two values that are quite high. So in that case, the most common, the first thing I would probably try to do would be to do a transformation to see if I could make the skewed variable a little bit more normal in terms of distribution, and see if that took care of the outlier problem and it made the kurtosis score better. But if that didn't help, then I would just leave the data untransformed and see if removing the extreme case or cases helped, because again, there's two cases here, right? 75 and 81. You take out one, you run it again and see if it's still an issue. Then if there was another one flagged, then that had a high z-score over 3.3, then you would take that out, run it again, see if it's still a problem, and so on. So in this case, I think that's what we would do. We would follow those two steps, see if we could make the data more normally distributed, and then in this case, as it says here, the best case in this practice would be to transform the data and see if that would address the skewness and kurtosis problem. Okay, so next we're going to look at the correlation between two variables. So I just want to point out, when you get a correlation table, usually you'll have a lot more than variables, but here we just have two variables. I want to point out that there's always a diagonal line through the correlation table that has the number 1. This number represents the relationship between the variable with itself. So sometimes people report a correlation of 1. This is not a real correlation. This is the number of, looking at the relationship between the number of admissions to the Children's Museum and number of admissions to the Children's Museum. Same with here. This is the 1 is the relationship between number of children and number of children. So that's not what we look at. What we want to look at is the data, not on the diagonal. So you can look at the data either above the diagonal or below the diagonal. It's going to be the same information. As you'll see, it's the same information on both sides of the diagonal. So you just either look above the diagonal or below the diagonal, and you look at the relationship between the two variables you're interested in. In this case, number of admissions to the Children's Museum and number of children. And we can see that there is a significant correlation or relationship between these two variables, with a correlation of 0.44. And the significance is in your output is 0.00, which should be reported as p less than 0.001, because it can never be 0, but it's just a very small number. And this indicates that it's really unlikely that we would get this relationship due to just chance if there wasn't a relationship between the variables. So this is suggesting that there is a moderately high relationship between the two variables. Okay, next we move into regression. In your regression you get a lot of regression output. So I'm going to break down these three tables in the next three slides. First, if we look at our model summary, we do get the correlation. Again, that's going to be exact same number if you just ran a correlation when you only have two variables. So in this case, the correlation is 0.44. The R squared is exactly what it means, the correlation squared, right? So but we translate this into a very useful number that we report in regression, which is the proportion of variance in the dependent variable, which can be explained by the independent variable. So in this case, what percentage of the variance in going to a children's museum can be explained by knowing the number of children? And the answer to that, we multiply this value by 100, and we determine that 19.3% of the variance in admissions to Children's Museum can be accounted for or explained by knowing the number of children. The adjusted R squared is an adjustment of the R squared that penalizes the addition of extraneous predictors to the model, so that doesn't really matter when you only have two variables. We can talk about this one more next week when we deal with multiple regression. And the standard error of the estimate is the standard deviation of the error and the square root of the mean square for the residuals in the ANOVA table. So this we typically would not report at this point. Next, I'm going to show you the ANOVA table. Even though we did a regression, the table is called an ANOVA table. So I don't want you to get confused by that. This is still regression. As you can see in the first line, it says regression. The second line says residual, and it gives you a lot of information. So the first column here, this is the key. You can look at this. The first column tells you the model, and it specifies the number of the model being reported. In this case, because we only had two variables, we just have one model. But we'll see in some future weeks where in this table you can have other models, because you can add additional independent variables or moderators or mediators, so this can look different. Or also curvilinear, you can test whether it's not a linear relationship. So there's different things we could look at, but since here it's looking at two variables, we just have one model. The next column is the sum of squares, and that's this is the sum of squares associated with the sources of variance. The total variance is partitioned into the variance which can be explained by the independent variable, and the variance which is not explained by the independent variables, which is the residual. Next, we can see the degrees of freedom. These are really important because we always report these. The total degrees of freedom is n-1, because remember, we always want to look at how many cases are free to vary. When we report our degrees of freedom with the ANOVA, we would report, the first degrees of freedom is going to be, the numerator degrees of freedom. I'm sorry, having difficulty speaking right now. And then the second degrees of freedom is the denominator degrees of freedom. So in this case, the degrees of freedom would look like 1,463. And that would be after we use our statistical abbreviation of F. Okay. And then the mean square, that's the sum of squares divided by their respective degrees of freedom. And then F, that's the statistic, which is the mean square for the regression divided by the mean square for the residual. And then the significance tells us, how this p-value does compare to some alpha level, which in this class and in many journals and statistics forums, we use alpha of 0.05. So in this case, our significance is p less than 0.001 because we see it in our output as 0.000. Okay, and then finally, the last box is the coefficients. This is going to be really important starting next week when we deal with multiple regression. But this week, because we only have one predictor, we can look at the number of children and how well that does as a predictor. It gives us a t-value and a significance. But when we only have one predictor, it doesn't give us a whole lot of new information because we already know from the previous slide that number of children is a significant predictor of number of admissions to the Children's Museum. But again, we should still report these numbers. You can report the beta value for number of children and the significance. And like I mentioned, in future weeks when we have more than one variable, we'd be able to look at these beta values and our significance, and we'd be able to see how well each predictor predicts the dependent variable. So I have an example in the helpful resources folder of how to write up a regression. So let me know if you have any questions as you go through that. And I look forward to seeing you in the classroom. And this was the actual beta value. I meant to circle this one. So anyway, I look forward to seeing you in the classroom. And if you have any questions, just let me know. Thank you.